Hey guys, welcome to this lesson on one-sided limits. Let's just jump right into it. So to begin, I have this function here, and I think it would be good for you to understand this lesson by pausing the video and drawing this yourself, and then hit play when you're ready. So here's what this function looks like, and this is like the perfect way to really demonstrate the idea of a one-sided limit. So let's start with the following three limit questions. So the first question says the limit as x approaches 2 to this plus sign. So this one says to this plus sign. Notice this one also goes to 2, but this one has a minus, and then this is just a plain old limit. So these are actually signs that are indicating which side of the function that you want to be on. And so this side means you want to approach from the right. Now, I have the memory of a hamster. So I am like prone to forgetting things like directions a lot. But I think this plus sign is actually really nice because it tells you more clearly kind of what side of the function to be on versus just the name. So first of all, just notice, so here's where we have here's my 2, right? So the right side is also the side that has more of, I always think of this as the more positive side. So if I look here at 2, so to this side or to this side has more positive numbers. This is the side that has more positive numbers. So basically then what this means is jump on this side of the function and follow along to where x equals 2 to see what value you get. So I jump on this leg here and I'm going along, and I'd say, oh, hey, it looks like on this side anyways, if this were all I were thinking about was this side, it looks like this would equal 3. So that would be the answer from the right. Now, going to this other one, so now this would mean, so you want to approach from the left. So let's see, approach from the left. Okay, so now, I always think of the minus sign as just, so again, if I think of this kind of 2 as a dividing line, so these are the more positive values on this side, these are the more negative values on this side, so this is the side of the function that I want to jump on. So if I'm on the left side, it just so happens that this now is kind of the function that I'm going to travel along. So using the left side of this function and now making my way to 2, it's like do, and then it looks like, oh, okay, if I were on this side, it looks like the limit should be approaching 1. And so this kind of resolves something then. So if I had just the limit as x approaches 2, so notice from the left side over here and the right side over here, it's approaching 2 different values. So this is what's known as a jump discontinuity. So the limit as x approaches 2 does not exist, but the one-sided limits do. And so this is kind of the lesson. Okay, so I want to give you a second to kind of think through this on your own. So now we're going to look at x equals -1. So I'll just go ahead and kind of mark this right here for you. So here's -1 right here. So take a moment just to maybe pause and think through these examples and then hit play when you're ready. Okay, so now I'm going to be on -1 from the right. So here I am. So again, this would be the more positive side. Everything over here is the more positive side. So then I would jump on, oh, okay, this is the leg of the function, and I just go up to x equals -1, and so this would equal 1 on this side versus -1 on the left. So now I need to be on the more negative side, so all over the values over here. Jump on this leg of the function, follow along, and now it looks like that the value I should be approaching is -2. And once again, just the value as you approach -1, since each side is approaching a different value, this would not exist. Okay, so this is kind of the conceptual idea. So just to make sure that you've really got it, I have this example here. So if you're really playing along at home and you're taking notes, which I highly recommend you do, you might want to pause the video just to maybe copy this down, and I've marked just some of the relevant points here, just in case you are gonna write this down. And so whenever you're ready, this is a little bit of a quiz here for you to make sure that you've really got the sides. So you can pause, take a second to think about it, hit play when you're ready. Okay, so I need to find the limit as x approaches 3 from the right. So here's 3. So now, once again, if I think about this as kind of dividing this in half, so let's see, I'll use this color. So here's my 3. So on the right side, that would be on this side over here. So that happens to be this function. So I jump on this leg, follow it along, and it looks like this value is, let's see, what's that, 1, 2, 3, 4? That's 4. So this will be 4. Versus from the left, so now I need to jump on this side of the function. So then I'm following around, and so it looks like on this side it's going to equal 2. And now, what is the value of f of 3? So this is different from the limit, right? So the actual value of f of 3 would be where that circle is kind of filled in. So right here. So this is the value of f of 3. So this would equal 2. So this is another very important distinction to make. Okay, so just to give you another chance at this, so I've got just a few more on here. I've got a couple questions in here, but these are really good for just kind of getting that directional sense for this. So once again, you can pause, hit play when you're ready. So this one, so I need to be -2 on the right. So here's my -2. So on the right, I'd be on this leg. Follow it along. It looks like this is coming to -2. So this will equal -2. Then I need to approach the limit as x approaches 4 on the left. So be really careful with this. This is one really common thing. So sometimes when you start seeing all these signs, people start getting kind of dizzy. And so you might read this as -4. This is 4 on the left. So like say that out loud to yourself if you need that. So if I'm approaching 4 on the left, so here's 4. Okay, so 4 on the left would be this side. And as I'm approaching, it looks like this should be going to 1. And if I approach 4 on the right, so then that would be on this side, and it still looks like it's actually approaching the same value, right? So this actually is still equal to 1. So this gets me to another part of my question then. So what is the limit then as x approaches just 4 of this function? Well, the limit of this is actually, it's the same on the left and on the right. So the limit of this is actually equal to 1. But what is the value of f of 4? Well, f of 4 is actually an empty dot. So this is empty spot here. So I'd actually have to come all the way down here, and I guess maybe my graph is maybe a little hard to read. So 1, 2, 3, 4. We'll call that -4. So we'll say f of 4 equals -4. Although if you said -5, I mean, it's, you know, I hand draw these, so sometimes it can be a little difficult to tell. So sorry about that. So okay, so this is what we've got, and this is kind of a good set of distinctions, and this also kind of illuminates another point about limits. So when does just a plain old limit exist? So we'd say that a function f of x has a limit, so it just has a limit in general, if and only if its left and right hand limits have equal values. So in other words, if I have some limit as x approaches c, so just plain old c, just a plain old number, and I know that the limit exists, what this means is that the limits on the right and on the left both have to equal the same thing. Makes sense when you look at a graph, but just want to kind of tie that out conceptually, or I guess theoretically. Okay, so now what I want to do is I just want to kind of walk you through a couple of calculations with one-sided limits, because sometimes people think, oh, now that I've seen the graph, this is going to become significantly harder. So not necessarily. So if you've already learned how to evaluate basic limits, a lot of the techniques just for evaluating general limits still work here. The only thing that gets tricky is when you know that you're going to have, how do I explain this? Basically, like the only thing that you have to worry about is when you know that you have a split like this happening on your function. So if this isn't happening on your function, you don't have some split value like this, then you don't have to really panic too much about how to evaluate. So let's take a look at a few one-sided limit problems. So starting with this one, so I've got the square root of x minus 2 over x plus 1, and I want to evaluate the limit as x approaches 2 from the right. So sometimes actually having the graph in front of you can be very, very helpful when you're first studying this, because you can get a little disoriented looking at these. So for instance, when I look at this, so I've got a square root, but I also have a fraction, right? So that kind of tells me two things. So for one thing, I can see by looking at this, so I can't, there's one value I definitely can't have. So x cannot equal 1. So this function does not exist at x equals -1. But then the other thing about the square root is that the square root itself, this whole thing, the value under the square root has to be positive. So maybe I'll kind of just mark this and say, so the overall value must be positive. So there's kind of actually a lot going on in this problem that can feel a little bit disorienting. And so if you think about this, if I plugged in something like, so if I plugged in something like 1, so just think about this for a second. If I plugged in something like 1, I would get 1 minus 2 over 1 plus 1. And this would actually give me something negative, right? This will give me negative 1 over 2. And the issue is that, so you can't take the square root of a negative number. So limits usually have to also go hand in hand with graphing. And we cannot graph imaginary numbers, so this wouldn't work. So there is a little bit of like some things you have to consider with this. But we are approaching 2 from the right, so that's important because this is the more positive side of 2. So maybe like an easier way to explain this would be to actually look at the graph. So let's take a field trip to Desmos.com. So this is Desmos.com, super awesome free graphing software. So it's a really great resource to use when you are studying calculus. So I just plugged in our limit. And sometimes when you're trying to wrap your head around this, looking at the graph is the best way to really efficiently do that. So check this out. Here's where x equals 2. So notice what happens. So anything to the left of 2, right up until somewhere around here, like does not exist. But anything to the right of 2 does. So it actually matters that our limit is one-sided because if I tried to approach 2 from the left, I have nothing to go from, right? I have like something going up here and I really can't, like if I just try to back out a little bit from this, like this just goes up for forever. So I really can't approach 2 on the left. I can really only approach it on the right. So that's kind of why it matters. But if I investigate this just a little bit farther, so notice the point does exist. It's 2, 0. So there's actually nothing, like as we approach from the right at least, there's nothing too special about this. So I know you don't always have the graph in front of you, but I'm just kind of bringing this up as a way to start getting comfortable with weird limits is using the graph. Okay, so let's go back to our problem. So now I want to show you kind of 2 ways that you can approach this. You know, so one will go the quick way. So you can actually, so just by looking at this, like I really can't see any issues why plugging in 2 is a problem in this case, and we're really approaching 2 from the right. So if I were to plug in 2, so just look at what happens. So I get 2 minus 2 over 2 plus 1, so I get the square root of 0 over 3. So I ultimately get the square root of 0, which is 0. So just like from a computational standpoint, this is a pretty solid problem. But the one thing that you kind of want to confirm is that 2 from the right is okay. So now the other thing that you can do if you're kind of struggling with a limit and you're like, I'm not sure, is it going to exist? Is it not going to exist? You can do a really quick inspection just to kind of make sure that this answer is going to work out. So here's how you do that. You choose a few values just to the right of that number. So just to the right of 2, if you think about the graph, would be 2.1, 2.01, 2.001. And so if you actually calculate all those values, you'll get these decimals. So I went ahead and calculated them and filled it in for you. So just kind of notice what's happening with the decimals. They are getting smaller and smaller as we get closer and closer to 2 on the right. So this really confirms that our answer is solid and also that this exists on the right. Now, just as a thought exercise to kind of finish out this problem, so think about what would happen then if I try to choose some values on the left. So what if I choose something just to the left of 2? Well, what's going to happen is I'm going to get 1.9 minus 2. I'm going to get a negative, and what you find on the left is that this does not exist. So if you're not sure, this is kind of the last thing that you want to do with your limit. You can kind of analytically go through and just notice the behavior as you get closer and closer to confirm that you found the right answer. Because if I said, let's evaluate this on the left, I'd say I could do the same thing and say it equals 0, but the problem is I don't have this other side of the story, right? So it does matter that it's on the right or the left. So in some ways, computationally, it can be very, very easy. It can be just as easy as calculating some of the easier limits, but it can also matter, right, that you kind of know some of this behavior. So it's simple and it's not simple all at once. Okay, so let's move on to the next one. Okay, so now moving on to this one. So this is another example where you kind of want to just think about, to begin, what values would maybe not actually exist here. So where would I have problem points? Well, in this case, my problem points would be at -1, 0, and at 4. And I have really, that is not the situation that I have, right? I just have that x is approaching 2. So sometimes when you have these limits that are one-sided, it's totally possible that you could get a problem that looks like it's going to be really, really difficult, and you really have to judge what you know about the problem itself. So in this case, I'm thinking about what I know about rational expressions versus in this last one, I had to think about both what I know about square roots and rational expressions. It was a lot to kind of put together. This one's actually a lot more straightforward. I know a lot about rational expressions. I don't really have to worry about this. So with this one, I feel pretty safe just kind of plugging in my number in this case. And I know it's not going to give me any zeros in the denominator, and there's nothing wrong if I get, say, like a negative value here. So this is one that I feel way more comfortable just kind of plugging everything in. Like, oh, and this is -1. And then this would be just 2. This would be 2. So if I multiply all of this together, I will ultimately just get -1/3. So I don't really have any problem points on the left or on the right. I don't have to worry about something existing or not existing in this particular case, but that's all totally due to the fact of just where this limit is approaching. So again, if you're not sure though, you can always look at the graph as a way to kind of confirm your suspicions, and you can also break out a table. So there's always a little bit of a balance when you're working with one-sided limits. So now for the last one, this is a pretty classic one-sided limit type problem. So the limit is x approaches -3 on the left. Okay, so I've got absolute value of x plus 3 over x plus 3, and then all that times x plus 1. So this is actually a really good example to look at the graph. So let's go back to Desmos for a moment. So here's what this looks like as a graph, and I know that you might be thinking, oh, but what if I don't have the graph in the test? But you just want to understand, once again, the behavior of how these functions work so that you have better intuition, so that you can make a more educated guess on tests and stuff. So this acts like absolute value, except it has like this break here. And kind of the thing to note about absolute value, just something that we know in general. So it has kind of two legs usually. And for simplicity's sake, let's say that this is the negatively sloped side and this is the positively sloped side. So these are both lines, right? But this side's negatively sloped and this side is positively sloped. And if you look at it, so where that break happens, it's right here at -3. Makes sense, right? Because at -3, that would make the absolute value equal to 0. So now let's talk about how would we work with this algebraically. So there's two ways that you can kind of deal with this. So first of all, we're talking about being at -3 on the left. So if I'm on the left side of this whole function, is that the negatively sloped side or the positively sloped side? That would be the negatively sloped side. And so what you can do actually is you can reinterpret your absolute value and force it to represent that negatively sloped side. So what I mean is you can actually rewrite this more explicitly as negative times x plus 3 over x plus 3, all of this times x plus 1. Now the reason that you want to do this is you cannot just cancel out x plus 3 when this is sitting in absolute value. You want to actually interpret which side of the absolute value that you're on so that you can then cancel it out like this. So I can actually make this nice simple cancellation now. And so then -3, so now I can actually just write this out like this. And now I can finish interpreting this. So I can just plug in -3 at this point. So this becomes negative times -3 plus 1. That will equal -1 times -2. So ultimately that equals 2. So that's kind of why you want to understand these graphs and how these things work, because it will help you to kind of decide and be more empowered for how you're going to break things down algebraically. But once again, if you're not sure about this, then what you can do is you can create a table. So if I didn't have a graph in front of me, then just what I might do to kind of back up my answer is I might just take a few values that are just to the left of -3. And if I fill this in, these are the values that I'll get. So you can also kind of see just by going at this approach too that confirms that this must equal -2. So A lot of teachers, me included if you're one of my students, so I prefer to see kind of this algebraic breakdown because this is much more precise than just using the table. But the table has its uses, and it can be a really good way to kind of confirm what your suspicions are if you're ever unsure. So I have a lot more examples of working with one-sided limits because I know that sometimes these can look like they're a little bit tricky. So feel free to check those out. I also have lots of videos on just general limits and all that good stuff. And if you have any questions, feel free to leave them in the comments. Thanks for watching. Hope to see you next time.